rocky filamentary structure of the cosmic web. And compare that to the region we've already analyzed. It's a much larger data set that we now have to play with. One of the things we've done is, in addition to using this data to probe dark energy, we can also use it to probe dark matter. And so here is a map showing you, again, that pinkish footprint on the sky, now superimposed on a picture of the southern sky from the telescope. And the little red dots are nearby galaxies that we discovered just last year. These are galaxies that are in our own cosmic backyard. These are dwarf galaxies. They're ultra faint. Some of them may contain only 1,000 stars or so, compared to the billions of stars in a typical galaxy. And these are satellites of our own Milky Way galaxy, much like the large and small Magellanic Clouds are satellites of our Milky Way. But these are much, much smaller, much fainter, and so we simply haven't been able to discover them until we've made this map. So we discovered 17 of these nearby dwarf galaxies just last year. And as I said, these little faint galaxies have the advantage that they're relatively nearby to us, to the Milky Way, and they're very rich in dark matter. They contain very few stars, mostly dark matter. And so we're searching in these dwarf galaxies to try to see the signal that annihilation of weakly interacting massive particles. So this is now a gamma ray image from the Fermi Gamma Ray satellite of one of those dwarf galaxies that we discovered last year. We don't see any significant excess of gamma rays coming from that galaxy, so that allows us to put constraints on the nature of dark matter. And finally, a couple of other sort of fun things that have come out of this, nothing to do with dark energy or dark matter. But when you make a large map of the sky, it turns out to be useful for a variety of other things that we hadn't even thought of when we designed and started the survey. Namely, we can use this, we think, to understand more about the nature of our own solar system, which is very nearby you. So in the upper left is showing you the inner solar system, the sun surrounded by the inner planets, then the asteroids, and then Jupiter. In the upper right, we're zooming out to see the outer solar system, including Uranus, Neptune, and Pluto, former planets, which we now realize is just one of a very large number of objects that we call Kuiper Belt objects. And in the lower right, we have a zoom out even further. So the solar system is now all contained in here. And in red is the orbit of an interesting planet called Sedna that was discovered a number of years ago. And Sedna, we think, is sort of has to do with, and then if we go up even further, we get to where we think that there's this vast cloud of stuff called the Oort cloud. And so it turns out that there's actually many hundreds of thousands, not only of inner solar system asteroids, but these Kuiper Belt objects, and more generally what we call trans-Neptunian objects, things outside the orbit of Neptune. And so here is a plot on the sky of the known trans-Neptunian objects on the sky, superimposed on the footprint of our survey. And then this is the orbits that they would trace out over a period of 5 years. And so basically this curve is just tracing out the plane of orbits of planets in the solar system around the sun. But you can see that a number of these things should be within the footprint of our survey, and we should be able to detect them because they move around over time within our survey. So if we take pictures over the course of 5 years over our footprint, we'll see some of these objects move around, and we'll be able to trace out these trans-Neptunian objects and learn more about the solar system. And in particular, these supernova fields are very good for that because we observe them roughly once a week. And so over the last 2 years, we've detected a number of these new trans-Neptunian objects by looking for things that move over the course of weeks or months through these fields over time. So this is a listing of all the new trans-Neptunian objects we discovered as of last year. There was a lot of excitement in the astronomy community a month or two ago because two astronomers postulated the existence of a new planet. You've probably heard about it, called Planet 9. This is a planet that would have about 10 times the mass of the Earth, and it's postulated because of the regularity of the orbits of a number of these trans-Neptunian objects, including a couple that were found with our camera. And we've been quite excited about this because if Planet 9 truly exists, we think there's a good chance this is the likely orbit. The orbit of this object is constrained by actually studies of the Cassini satellite orbiting around Saturn. If there was any additional mass out there, it would show up as a perturbation of that orbit. And so the most likely range of orbit for this Planet 9 directly crosses our survey footprint. So we have people in our team now trying to use our data to see if we can see any trace of this possible hypothetical nucleus. And finally, as Andre mentioned, there was a lot of excitement last month with the announcement of the discovery of gravitational waves. This is a sort of warping of space-time that was predicted by Einstein's theory of relativity 100 years ago. And basically, what they discovered was the signal, the chirp, due to two black holes, each 30 times the mass of the Sun, orbiting each other and eventually spiraling in and merging. And that's a very violent event from the point of view of space-time. It sends out these ripples of space-time, which were observed by the LIGO experiment using these two huge detectors, one in Washington State, the other in Louisiana. This is quite exciting, and LIGO is now going to turn on again later this year. And we realized that LIGO was going to be turning on last year, and so we formed a project using our camera and our survey, such that when LIGO said gee, we think we maybe have seen something, we would go and point our camera in the direction of the sky where they thought it was coming from, and see if we could see an optical light counterpart to these gravity waves. Now the problem is that with only two detectors, one in Washington and one in Louisiana, they couldn't determine very precisely where on the sky these gravity waves were coming from. To triangulate, to really determine the direction precisely, you need 3 points at a time. They only had 2. And so they had a rather large uncertainty in where on the sky this was. And so within a couple of days, we pointed our camera at the most likely region of sky where LIGO said they thought they saw this event. And we were searching for an optical counterpart. We didn't see anything. That's not too surprising because if they're black holes merging together, it's unlikely that you would form something that would give off optical light. However, in the future, LIGO will be sensitive not only to black holes merging, but also to neutron stars merging. And we think there's a good chance that when neutron stars collide together, they would give off optical light. So we will hopefully continue this program in the future. It kind of piggybacks on the survey that we're carrying out and synergizes with it in a nice way. And so our hope is that in the next year, perhaps, we may be able to discover optical counterparts to the gravitational wave events for the first time. This is a picture of the Orion Nebula. This was taken with the Dark Energy camera. It has nothing to do with cosmology, but I thought it was a pretty picture. And this also has nothing to do with cosmology. This is a comet. So when we're pointing, a computer tells us where to point the camera on any given time and any given night. Our computer doesn't know about comets, and so there just happened to be this quite bright comet, Comet Lovejoy, that was passing through while we took the picture, and so it makes a nice, pretty picture. All right, to summarize, the universe is about 13.8 billion years old. It's about 95% dark, 25% dark matter, which holds galaxies and clusters together. There's going to be a quiz at the end. About 70% dark energy. It's filled with billions galaxies and clusters of galaxies that are mostly dark matter. It's expanding from a Big Bang. That we've known for quite a while. For the last 18 years or so, we've known that that expansion is actually speeding up. We don't know why, but it's likely due to this dark energy, which makes up 70% of the universe. And with the Dark Energy Survey and other surveys that will follow onto it, we're embarked on this journey to address this mystery, to try to understand, learn more about the history of the expansion of the universe, and therefore hopefully learn more about the future evolution of the cosmos. Thank you.
Questions for about 20 minutes?
Sure. So I think there are people under some questions. There's a few folks with microphones, so just raise your hand and they will find you.
Thank you. The question I have in the pictures you've been showing us from the Dark Energy camera, how long is the exposure when you're making those images?
Okay, good question. So how long is the exposure? So in 4 of the 5 filters, our exposures are 90 seconds long, so a minute and a half. In the very reddest of those filters, we expose for 45 seconds. So each time we expose, we open the shutter for 90 seconds, close it, move the telescope point in a different direction, open it for 90 seconds, close it. And so their individual exposures are 90 seconds. But as I said, over time, we come back and revisit each part of the survey field 10 times in each of the filters. So by the end of the survey, each part of the sky will be covered 900 seconds of filters. Yeah, then we layer them on top of each other, called co-addition.
Thanks for the great talk. It seems like the total energy of the universe is increasing. If that's correct, what happens to the law of conservation of energy?
Good question. So that's true. If dark energy is the dominant stuff in the universe, as I said, when the universe expands, the density of dark energy isn't going down. So therefore, so the energy per unit volume isn't decreasing. If the volume is increasing, then the energy would be increasing. So what happens to the law of conservation of energy? It's not true. Sorry. And actually, we've known that for going back way. So in Einstein's theory of relativity, energy as a global quantity is not.
Yes, at the beginning of your talk, you said that your father's objects are 30 billion years, 30 billion light years away.
Yeah,
how can that be if the universe is only 32.8?
Yeah, I knew I was going to get that question. Good question. So it really comes down to how do we measure distances? And the point is, so, we measure distances with rulers or tape measures or something, right? That clearly doesn't work when I'm talking about things very far away. And so there are different ways to measure distances. So depending on those different ways of measuring distance, I can use the brightness of an object, I can use the apparent sizes of objects, and those give me slightly different answers. So the 30 billion years was using one particular measure of distance that doesn't mean that that anything moves faster than the speed of light. It's just due to the fact that when I get to very large cosmic distance scales, it takes a long time to measure that distance. And so depending on how you define distance, you can get different answers. No, it's not inaccurate. It just means that when I get to cosmic distances, when I tell you the distance to something, I also need to tell you which distance I'm using. As long as I tell you which distance I'm using, it's fine. Trust me. Over here. Over here. Here we go.
So the ratio between dark energy and just regular matter, did you actually get that by looking at the amount of matter that there is, figuring out how much energy you need to accelerate to match your observation, and then just do the energy equivalent of that, and then just take the ratio?
Yeah, exactly.
We need to talk later.
That's it. Over here.
What's the difference between dark matter and gravity?
What's the difference between dark matter and gravity? Okay. So gravity is a force. It's an interaction. So gravity is anytime you have mass or energy that creates a gravitational field, which exerts a force on any other body moving in that gravitation. So gravity is the thing that dark matter causes. Dark matter is just stuff. It's mass. It's something that has mass that is dark. Beyond that, we don't really know what it is, but it's not in itself a force. It is. So in elementary particle physics, we have the basic particles of nature, the quarks. Those are the stuff that all matter that we see is made of. And then we have the interactions, the forces between them. And gravity, so we usually talk about the strong force, weak force, the electromagnetic force, and then there's the gravitational force. And so basically our picture of how physics work is that it's elementary particles interacting via forces. So dark matter we think is likely to be a new elementary particle. Gravity is one of the forces through which they interact. Microphone. Back here. I can repeat. So the question is, does that mean that dark matter does not produce gravity? No, we think dark matter does produce gravity. Any form of mass or energy produces gravity. But it's just it's not the same as gravity, which is what the back up here.
Close. How close is our closest galaxy neighbor?
How close is our nearest galaxy? Well, some of these very faint dwarf galaxies are only tens of thousands of light years away. The largest big galaxy to ours, the closest one comparable in size to the Milky Way, is Andromeda, and that's about 2 million light years away, give or take. Galaxies, the typical separation in space between large galaxies is a few million light years.
So if we were trying to send a deep space mission to the Andromeda galaxy and the universe is expanding at 3,000 miles per second.
Okay, good question.
That like you keep cutting the distance in half every time you never get there?
Yeah. Well, first of all, it would take a really long time. I know there's some people who are happy to go to Mars and not come back, but that would anyway. Although actually, so with Andromeda, I can sort of give you an answer without actually answering because. So I said all these galaxies are expanding, moving away from our galaxy, and that's true of almost all galaxies. It's true of all distant galaxies. Andromeda actually happens to be gravitationally bound into a pair of galaxies with the Milky Way. So actually Andromeda is approaching us, and we think that eventually Andromeda and the Milky Way will collide and merge together in some number of billions of years. So actually, if you wanted to just go to Andromeda, then you could just wait a few billion years. But it's true, if you wanted to go to other galaxies, then yes, you have to go fast because they're moving away from us. But you can move faster. They're not moving faster than the speed of light, so we think you can get them. Left-hand side over here.
What's your favorite part of studying dark energy?
My favorite part?
Yeah. Why do you study dark energy? What got you started in it?
Oh, good question. Well, actually, what got me started studying dark energy was, by training, I'm actually, and most of my career has been as a theoretical astrophysicist. And there was sort of indications going back to the early to mid 1990s, before the supernova discovery, that things were not quite right. That we already had sort of tentative evidence that this picture of a slowing down universe wasn't quite holding up. So it's sort of pre-evidence, if you like, for what we now know is acceleration of the expansion. And I had, in my earlier career, focused on, so I mentioned in one of the slides that we think there was actually a much earlier epoch of very rapid expansion called primordial inflation. So we think that a tiny fraction of a second after the Big Bang, the universe was also actually speeding up. And then eventually inflation ended and it went into a decelerating, slowing down expansion until dark energy took place. So we think that this is actually at least the second time in cosmic history that the universe is speeding up. And I had worked earlier in my career on some hypothetical ideas for what could be causing that earlier epoch of cosmic speed up, inflation. And so with some colleagues here, we started thinking about, well, gee, what could that same kind of phenomenon, I mentioned this very light, super light cousin of the Higgs boson, could that be causing the current epoch of cosmic acceleration? So that's really how I got into this study. And then in the late 1990s, the discovery of the direct evidence for cosmic acceleration from the supernovae got me into thinking about, okay, how can we test this idea? How can we learn more about it? Theorizing is great. I love theorists. But there are certain times when you just need more data to really make progress in understanding. And my judgment has been that in dark energy, we really need to do these kinds of surveys to point us in a particular direction.
Thank you. My question is related to your slide, which shows percentages of dark energy, dark matter, and normal matter over the course of 13.7 billion years. Now, the slide shows that originally there was 17% of regular matter. Now we have only about 5.
Right.
How do you explain this reduction, or in the amount of regular matter? Where it appears?
Okay, so basically, so the universe is expanding, and as any kind of, if you have a gas that expands, right, it becomes less dense. The distance between particles of the gas is increasing in time, so the mass per unit volume of that gas is decreasing. The universe is expanding, and so the density of ordinary matter and of dark matter we think is going down. So that's not surprising, but what's surprising is that we don't think that's happening for dark energy. As we expand the universe, dark energy seems to have this strange property, at least according to Einstein's theory, that as you expand it, it doesn't become more dilute. And therefore, as I look at different epochs of cosmic history, the relative density of both ordinary matter, atomic matter, and dark matter relative to dark energy is decreasing. It's decreasing, they're both decreasing at the same rate.
By the way, for a moment, it looks like we are losing the atoms, from our,
Yeah, we're not losing them, they're just moving away from each other. They're still there, they're just farther away.
Well, so it's a density that's different, not the amount. So what are we measuring, density or the...
Yeah, so think of it as density. It's the amount per unit.
What's the difference, the mass versus density?
Yeah.
Thank you.
Left-hand side of the center section over here. When you look at the fact that the universe is expanding and accelerating, that to me would imply that observers in our local group with 100 billion kilometers of light years from now will not be able to see the universe as we observe it. Should we not record something for them to see the beauty of it today? Because they're going to see a lot less of it.
That's true. So, yeah, that's a good point. In 100 billion years, we think the only galaxies we'll see will be the galaxies that are in our local group. So the ultra-faint dwarf galaxies, the Magellanic Clouds, and Andromeda by then will emerge in the Milky Way. but it'll only be a handful of very local galaxies that are bound to our Milky Way Andromeda supergalaxy. All the other galaxies, the billions of galaxies that we see today, will have expanded beyond our horizon. And so not only will we not know that the universe is accelerating, we won't even know that it's expanding. So I agree we need to not only record this for future generations, but this also adds a great urgency to these kinds of studies. We need to fund them now. Because we only have 100 billion years to answer the question. And it's a really hard question. So, it could take that long. So, yes, thank you for bringing that up.
Fifth row center here.
So I wanted to go back to the relative density. Did you arrange the amount of dark energy to be approximately the size of the known universe and the various elements?
No. So what was assumed there was just that the density, the energy per unit volume of dark energy wasn't changing. Now, we don't know that that's strictly speaking true. It could be changing a little bit. It could be decreasing a little bit. Could actually, in some bizarre theories, could actually be increasing. But in that particular case, we were just assuming that it was true.
So that's the result of those numbers.
Yeah, that's right.
We don't have measurements to
That's right. Yeah, we don't. I can't. Yeah. So yeah, I should be clear. When the universe is 1 billion years old, I can't tell you that it was precisely 1% dark energy and not 2.
Fourth row right over here.
This is to piggyback on a couple of earlier questions about dark matter and whether it exerts gravitational forces.
Okay.
I think you had, in one of the earlier slides, you had said that the model for a galaxy would indicate that the stars on the outer edge are moving slower than they, or should be moving slower than they actually do.
If there was no dark matter.
Right. And then the planetary bodies within the solar system, do they conform to the expected model?
Yeah.
So is that an indication that the region of space that the solar system exists in is relatively devoid of dark matter?
Good question. Very good question. So the answer is no. That in the following sense. So it's true. When I calculate the orbits of planets around the sun, I never take into account dark matter. Why is that? It's not because we think that the local region, the solar system, is somehow deficient in dark matter. It's just that the density of dark matter in our galaxy, in our solar system, is much lower than the gravity of the dark matter, if you like. It's much weaker than the gravitational forces. And so the sun is by far the largest component of mass in the solar system. The amount of mass of dark matter in the solar system. So we don't. We think it's stable, but it's just a negligible increase in what's already there.
Can you comment on the theory of dark energy changing into dark matter and vice versa? Is there any evidence that you found?
Yeah, so there are some models, theoretical models, where they try to relate dark matter to dark energy, perhaps have them maybe transmute into each other in some way. We certainly, haven't been able to do any observations yet that provide evidence for against. I should have mentioned that we have no good theory, accepted consensus theory of what dark energy is. So that means we actually have thousands of theories of what it could be, and that's one of them. But we haven't been able to really test that.
A couple more in the back over here.
Whatever happened to modified Newtonian dynamics as an explanation for all this?
Yeah, good question. So back in the 1970s and 80s, when Vera Rubin was doing her work finding that galaxies were spinning faster than they should be, most astronomers said, okay, there must be this additional stuff. We call it dark matter. They remembered Zwicky's work from the 30s that had shown the same thing in clusters of galaxies. But on the other hand, some people say, well, gee, I can't see this stuff. Aren't you just making stuff up, like, epicycles to explain the orbits of planets? Could it instead be something going on with our understanding of gravity? So there was a theory called modified Newtonian dynamics that Israeli physicist Mordecai Milgram showed that if you modified, so in high school physics, if you've taken high school physics, you learn this famous Newton's second law, right? F equals ma. A force you apply on a body of mass m causes it to accelerate with an acceleration k. What Milgram showed is that perhaps at very low acceleration, F equals ma is wrong. It gets replaced by F equals m times some other function of the acceleration. And he showed that if you make that function the correct form at very low acceleration, you would get those same rotation curves for galaxies that Vera Rubin and her colleagues found. So this is called modified Newtonian dynamics. And I would say when the only evidence we had was, rotation curves of a small number of galaxies, Zwicky's work on Coma, then you would have said, okay, yeah, maybe it's dark matter, maybe it's modified Newtonian dynamics. What's happened in the decades since then is that we have a huge abundance of evidence, all pointing to the same picture of 25% of the universe being dark matter. We have the gravitational lensing maps I showed you. We have merging clusters of galaxies where we clearly see that the mass is not where the gas in the cluster is. And we have the cosmic microwave background pointing to a universe that again has a spatial geometry that's spatially Euclidean, and so we need to have enough matter to make that up. And so that we now have a whole host, we have the whole picture of how galaxies form, that simulation I showed, which relied crucially on there being dark matter interacting by gravity. So we now have this whole beam of evidence from microwave background, large-scale structure, gravitational lensing, plus many more studies of rotation curves of galaxies, clusters, all pointing to this picture of a universe that's 25% dark. And so I think just the modified Newtonian dynamics is sort of an interesting observational, sort of almost phenomenological law, if you like, that galaxies appear to obey, but it doesn't hold up as a sort of theory itself. I think the preponderance of evidence for dark matter is now.
We'll do two more. Here. You mentioned that there was evidence of expansion of the universe. Does that mean we have evidence that there was a period when of contraction, everything went back to the single point of origin leading to the Big Bang?
So our current picture is that the universe, since the Big Bang, has been expanding. It's been expanding at different rates. We think shortly after the Big Bang, it went through this accelerator expansion, then the expansion slowed down for a while, and then a few billion later started speeding up again. That's where we are now. We don't have any. The picture of a contracting universe would be perhaps before the Big Bang. There was an earlier period of contraction and then expansion. There's been a lot of theoretical speculation about that, but we don't have, as yet, any direct observational testing.
And the back left over here.
And can you touch on what you found at Triangulum 2?
I'll go in your boat.
The dwarf galaxy. Yeah. Sorry?
Imagine being able to do that. It's like a lot harder.
Yeah, it said it had the highest proportion of dark matter. That was in a Mars astronomy with quantum.
Okay. I'm not sure exactly what you're referring to, but there are, I think you're talking about one of the dwarf galaxies, right? Yeah, so these dwarf galaxies that I mentioned have relatively few stars. They're mostly made of dark matter. and we're still trying to, so we can discover those galaxies. We then need to follow them up with other sorts of observations and really study them in detail. We're starting to do that now with a number of these. And then the other thing we can do is to search for gamma rays from them to see if there's dark matter annihilating their core. So one thing I sort of, in passing, so far we've seen no concrete evidence of dark matter annihilating in the cores of these galaxies. From other people analyzing the same data, well, so there are sort of fluctuations in a few of these galaxies where you see some gamma rays coming from them. We don't think that's strong evidence for dark matter annihilation. Other people get more excited. I'm not sure if that's what you're referring to.
I think we have one more in the far back, if that's okay, John.
Yep. All right.
Thank you.
Maybe it's good I'm asking the last question, perhaps because the question I'm going to ask is to speculate on the end of the universe as a result of dark energy. Okay. Not rehearsed. Professor will tell you that we're not working in concert. So what I understand is, or at least my understanding of it is, that eventually as gravity, dark energy, assuming it continues to do what it's been doing, pulls the universe further and further apart, gravity will have less of an impact on every body, including shaky ground, sir, including atomic nuclei. And so, is that what the big rip is?
Okay. Yeah. Okay. So it depends on the nature of dark energy. If dark energy is just the energy of the vacuum of empty space, then we think the future scenario is going to be what we were talking about earlier, that eventually all the other galaxies will just recede away from us. We'll end up with this universe of our galaxy, a few neighboring galaxies. Otherwise, the laws of physics will look pretty much the same. There is a possibility, I just briefly mentioned it before, sort of an alternative theory to dark energy, which is not that. So if the dark energy is the energy of the vacuum, then as the universe expands, the density, the energy per unit volume of the dark energy has to change. The big rip is a hypothetical alternative model where actually as the universe expands, the energy per unit volume, the density of dark energy, actually increases. Now if that happens, then not only is the universe speeding up, but the speeding up is speeding up. And eventually, in that case, this repulsive force will not just push all the other galaxies away, but it will eventually become the dominant force even on human and subatomic scales. And it will basically overwhelm all other forces and basically rip all particles, all atoms in the universe to shreds. So that's why they call it the Big Rip. So that would be quite a spectacular end to the universe. It would basically just everything would blow apart. Again, we don't think that'll happen for tens of billions of years.
So I see Orlando gave the mic to someone over here. Do you mind doing just one more? Okay.
Is there any preliminary results that you can mention?
Yeah. So I showed you some sort of pictorially some of the results. We don't yet have any preliminary results on dark energy, on the nature of dark energy. We're hoping in the next year or so. Now that we've got a large amount of data, we're busy analyzing that now. And so my hope is that by next summer or next fall, we'll be able to say something interesting about the nature of dark energy.
Dr. Josh Freeman, ladies and gentlemen.
accelerators are used in a large number of areas for applications now, but what we're interested in is moving that whole story forward with the fact that the technology of accelerators is advancing rapidly, and that Fermilab is kind of pushing the envelope on that. And then, as you heard together with Argonne, we think that we're really dealing with new technology now that can be applied to almost situations that we haven't really thought about. So we're going to sort of probe into that area. So today, some of our goals will be to announce the launch of the DOE Accelerator Stewardship Test Facility Pilot Program. That's, okay, long name, to promote lab, industry, and university partnerships on accelerators and related technology. So this is a new direction for the government. It's not something that existed, should say federal government, new direction for the federal government, in that they believe there is an opportunity here, and this has been growing over the last several years. So this is not a new thought, but it's a new initiative, and it's finally getting some funding. It has rather strong support in the Senate, so we see this as a program that's going to grow in the future. We want to inform you about laboratory technical capabilities, understand your biggest challenges and whether a partnership might be useful to address them, and discuss possible partnerships with some of you we know and some of you we don't know. Part of a larger effort to encourage national labs to partner with industry to promote innovation and U.S. industrial competitiveness, launch new industries, and create jobs. So that's the thrust of this program, and how that plays out will depend on how we do, I think, in discussing where we want to go. These approaches have been used elsewhere successfully, for example, Germany, and they've been recommended by a number of, I'll call fancy committees. Blue ribbon panel is a nice way to say that, but a lot of people think this has great potential. Okay, so here's a nice picture of Fermilab. You can see we one time had the world's highest energy accelerator, the Tevatron, which has now passed the baton on to Europe, to CERN as the highest energy machine. But we are now producing the most powerful neutrino beams in the world here, so we've been moving in the direction of high intensity rather than high energy. And so that, I think, has the greater application potential to the private sector than just going to higher energy all the time. So that's basically the strategy. So to carry out that mission, Fermilab designs, builds, and operates high energy, high power, high reliability accelerators. And I would say in combination with Argonne, we address quite a broad range of accelerators. We address different technologies, different capabilities, but in the end, I think we cover soup to nuts in almost everything that goes on with accelerators. All right, so at Fermilab, we build state-of-the-art accelerators to understand our world via particle physics. I'm not going to spend a lot of time discussing quarks and leptons to you. I'm sure you've already read up on that. So, but there have been many, many discoveries over the last 40, 50 years related to understanding basic nature using accelerators, and I think that's the message. We use them as tools of research, but they can be used for other purposes. So that's all the particles that were discovered with accelerators. And in particular, if you go to this, we call these families, first family, second family, third family. Fermilab discovered the top quark, the bottom quark, and was the first to observe the tau neutrino. So 3 of the 4 in the last family were discovered here. So that's pretty amazing. Compliment to my colleagues from the past. Despite their impact on science, most accelerators that have been built are used for other purposes. So there's about 30,000 accelerators in use around the world. Sales, big number here. Accelerators touch a huge number of products in terms of their revenues or sales, and they're a major impact on our economy, in our health, day-to-day health, and well-being. So some of the products you see here are I'll go into a little bit of detail, but not too much. Hardening of tires, electronics, wrapping of various kinds, electron beam welding, and so on in the aircraft industry. So lots of applications that you probably haven't thought of. Okay, so accelerators are essential tools in industry. So ions are implanted into various metals to harden tools, reduce friction. Materials for implants. They're used to harden surfaces, modify optics, improve the quality of various gems. They're used in solvent-free printing, which is environmentally friendly and the direction I think lots of people think we should be going. Food irradiation, I'm sure you're familiar with, and medical accelerators. Okay, so a wide range of industrial applications make use of low-energy beams of electrons. So electrons are used to drive chemistry. These are low-energy numbers for a place like Fermilab. We barely understand this lowness, but that's okay. But the megawatt is the challenge. So when you think about power, it's going to be the energy times the current. So we're talking about high current accelerators. So electron beam irradiation improves heat resistance of coatings, wires, cables, cross-linking polymers. So what you're seeing here is the electron is used to break the bond so that you basically form a new structure in the polymer so that you have a harder material, and that's what's used with radial tires. You can see there's 1,500 dedicated facilities around the world doing things like that. Okay, on this slide we're showing the impact of electron beam welding and machining, and it's used in all kinds of things in your car, for example, in jet engines, in turbochargers. You can see roughly the size of a electron beam welding machine here in that picture by Pavis. Accelerators are used for national security, so here you've determined that there's an old car sitting inside of this container, so that must be interesting to the government. More than 2 billion tons of cargo pass through U.S. ports and waterways annually, and accelerators are used for cargo scanning and active interrogation to detect special materials. And we've talked about using other particles than just X-rays, so there's actually potential for doing more interesting things, I would say. Accelerators in medicine, I'm sure you're all familiar with proton cancer therapy, where you're using protons rather than X-rays. The seminal paper on this subject comes from Bob Wilson, who was the first director of Fermilab, who pointed this out as a possibility. And the first, I would say, facility-located machine was designed and built at Fermilab, and it's been operating at Loma Linda in California for decades now, working well. There's a worldwide industry in this now, and it's obviously had a big impact. So there's other technologies. People are looking at smaller technologies using superconducting technology to make things more compact. And this is still a very, very much a growing field. Okay, so that's what exists. Now, future accelerator applications are envisioned. So we give you a significant number of ideas that I would say that we've been thinking about. So there's the energy and the environment associated roles that you can use accelerators in, more industrial, medical, safeguards, and security. And I'm going to go through just a few of these for you. So, but one of the principal ones is the fact that accelerators can drive chemistry. So you're going to use the electrons from the accelerator to adjust the bonding of various molecules. The way it's done traditionally is that you heat things up, and it's a very inefficient process. And so you have to heat up the material or the gas or whatever to give enough energy to the system so that the bonds break, the electrons are ionized, and a chemical reaction can take place. Or you can use an electron beam to actually knock the electrons off, which is much more efficient. So that's the basic idea, is that you have a high enough energy electron to ionize the atom or the molecule that you're interested in modifying. So accelerators can be used for the environment. So here's an example with water. So they're effective for destroying pesticides, organics, pharmaceuticals. You can use them for sterilizing municipal water, for example, or sludges. It allows water to be reused, and of course water is becoming a super valuable resource. It's the oil of the future in some sense. So I see this as a potential significant growth industry. Beyond energy, the availability of clean water is the next crisis, and I think most of the planets figured that out already. Technology demonstrations are available, but they're not really deployed. And the question is why? Well, it's just the way we organize ourselves within municipalities. So a small township, say, would have to go out on a limb to put in such a sophisticated facility. So you need some kind of assurance that this is going to work. They're not going to be by themselves. So we think there's ways of working with multiple municipalities that this could be something that becomes quite practical. It should be reliable, could be compact, efficient, high power. So we're showing you in the upper right-hand corner the technology that Fermilab is putting a lot of effort into, as well as argon, and that's called superconducting RF. So it's superconducting material. It's a solid niobium that runs at cryogenic temperatures, and we think you can make compact systems using this technology that would be quite practical. Accelerators can be used for other things. So here you're seeing a picture of the night, satellite picture of the U.S. at night, and most of these bright spots are towns or cities, but this is actually the gas in North Dakota being burnt off, so we just waste it basically. So many wells produce both oil and natural gas, but not all the gas is recoverable. The locations are very remote, so the pipelines are not very economical. They produce a burst of gas for only a few years, so that's why it's flared off. And as you know, methane is not good for the environment. So the worldwide business here, if you like, is $30 billion a year of gases flared. So it's almost unbelievable. It's equal to 25% of all natural gas usage in the U.S., and it's doing no useful work for us, and of course it's bad for the environment. There are techniques to deal with this, but these are very big, complex, difficult systems to put in remote areas. So this hasn't clearly caught the attention of industry, and so has not really caught on to be used. However, we think mobile accelerators could, in principle, be used to efficiently convert the gas to a liquid. So that's the basic idea. You would have a portable system that would, say, be on a tractor-trailer arrangement like I show you here. So the trailer-mounted high-power electron accelerators, by going back to the technology we're developing now, it's kind of state-of-the-art technology. The natural gas can provide the local power, and then liquid hydrocarbons can be created and can be mixed and collected with crude oil produced by the well. So there is a strategy to do this. I think it needs to be developed further, but has significant potential. And you can see the amount of single well flares in 1 to 2 years. So it's on the surface of it, it looks like it's a plausible business model put together. Coal, of course, is still a major source of electrical power in the world. Sadly, I think China and India are ramping up use of that. The U.S. EPA regulations will reduce coal, but it will remain an important energy source regardless. And so removing and cleaning emissions from burning oil is essential. Removing the NOx and SOx, and there's techniques using electron acceleration.